Okay. So it is the morning of the 22nd day of Advent of Code. I finished the first part of the day 22 problem, moderately quickly last night, and I just completely flailed around on the second part. And in fact, I actually, once I went off camera, I went off and I took the dog out and everything. I came back and like this geometric thing about cubes that intersect and you can decompose cubes, and I was sure that it could work. And so I spent something close to another hour futzing around with all this code to create these cubes and then figure out whether two cubes overlap with each other. And then the key was this deconstruct thing where you take two cubes, and I realized that the combination of two cubes can be broken into 22 cuboids, can be broken into 27 regions. And each one of those 27 is in either none, one, or both of those cubes. And so you can just, deconstruct those two cubes into the 27 regions and then assign them to particular sets. And then, if you can do that, which is fairly straightforward because you don't have to consider all 27 things, you just generate them all, and then as a hack, you can just pick a point in each of those cubes and see whether it falls within the two cubes. So this is actually, even though, we got this impressive loop here, but this loop is just setting up the 27 things, and then once you have that, you can go through and, the number of things that are on can just be a sequence of non-overlapping, which is quite important, a sequence of non-overlapping cubes. And then every time you have a new cube, you map it against each one of those cubes that has the lights on, and you either add on additional cubes to the on set, or remove cubes once you've broken them down. But then, of course, you have the problem with, well, you're potentially in the process of doing that. You're breaking down both the new cube and the existing cubes into bunches of smaller cubes. You have to keep updating those sets. And so I started writing some code, but I didn't quite finish it. And I do believe that this approach is viable. But this is crazy. And I could talk, tonight, assuming I feel like doing day 23, I, might talk about exactly how crazy that is. But if you go back to it, the initial problem was very simple. Like the process was very simple. You just have these ranges of numbers and you turn them on and off in this set. And, going to bed last night, because even the hour I spent doing this, I knew it was not a good approach, but there's a certain amount of a general purpose, clever approach that is genuinely appealing to me. Like, if I had this problem at the office, and I had, and this was like an important thing to do for a several month long project, I would absolutely pursue this because it helps you understand all the problem better. Even if you come up with a simpler approach, the way I at least develop understanding is by generally trying to do this. And, and this is what I was mentioning before, people who do a lot of geometric programming have excellent intuitions for things like overlaps and rotations and everything that I simply don't have because I've never done much of that. But anyway, the point is, there is a simple way to do this. And my first thought, as I was kind of lying asleep, hating myself for being both a bad programmer and a bad algorithm guy, I realized, well, you know what? The numbers are fairly small. So what if we just eliminated one dimension? Like, we did the completely dumb approach for X and Y, but for Z, Z to Americans, we just did some run length encoding on one dimension. And so that makes you think, well, that's actually pretty straightforward, right? The data structure for saying instead of, you mark out every integer between two numbers, and associate a Boolean, whether it's on or off, with that integer. Well, instead, you just have a set of intervals, right? But then it occurred to me, well, if you're going to do that anyway, you can actually do the same thing for every one of your dimensions, because if you run length encode the x, so you have a range of integers there, then there are probably going to be a bunch of ranges of y that have the same set of ranges of z, and the same thing for x. Now, is this totally the same as keeping a collection of like non-overlapping cubes and so forth? It's not quite the same, but there is an interesting relation between the two, and I haven't worked out what might be beautiful theory of the relation between those two. But I do think that just implementing simple run length encoding is probably quite a straightforward and possibly quite quick to implement way to solve this fairly modestly sized problem, right? And so I'm kicking myself for going for the hard thing. And again, I can talk later about why I was doing that. So anyway, so let me try to implement that and see whether it's viable, implementing this kind of range-based data structure and then applying it to a quite naive approach to turning off sets of lights, right? So, I will, this code that doesn't work, I will push it into the repository if you're interested in like a very overcomplicated way that still does not work. But you can see the bones of what I was doing. Anyway, let's get rid of that. Instead, let's call this 2.runLength Swift, right? Okay, and let's make this big enough that everyone can join in the fun, right? So, we will get to, in fact, this logic looks complicated because of all these 50s and everything. The structure of this code is going to look quite different, so let's not bother with that right now. Let's instead focus on, what should we call it? We'll call it a, should be a struct. Let's make it a struct. We might, for efficiency reasons, we might turn it into a class later on. A range dict, right? And we're going to say, actually, equality comparable. I don't know what that protocol is called, so equality, come on, element equal, come on, I want the, where are the protocols that it conforms to? Related type aliases, no, initialize, conforms to, comparable, no, oh, it might be, oh, equatable. So, conforming to equatable. So all you need is your stored properties, so that's fairly trivial, right? So, equatable. Good. So, something is rattling again. Okay. So, what are we going to have in this? We are just going to have an array of points and their values, right? And I think the goal here, actually, let me, no, I'll do that after I explain what I'm doing. The point here is to say, let's say the meaning of this is everything above the key has given value. So if like the key were, oh, it's not a dictionary, we're going to actually make this an array of tuples. Let's make that an array of tuples. Oh, are tuples equatable? They've got to be equatable. Let's check that. Yes. Okay, tuples seem to be equatable. That's reassuring. So if like you had an array that consisted of nothing but int min. Oh, there was one. Yes. Nothing but int min and the value true if t were a boolean, then that would say that everything above int min were true. If you had two elements there and it was like int min and then 5, then int min was associated with true and 5 was associated with false, then everything up to 5, not including 5, would be true, and everything from 5 and up would be false. That's the semantics I'm going for with this array here, right? So one thing I want to know, can we just use the default constructor for t? So let's see if there is a default initializer. There is, and it's false. That's great. Okay, so in that case, we can just have a default initializer here. Oh no, we don't need that because we can just actually do it here, can't we? Equals array of int min, is that a thing? And then, okay, so let's see if that compiles. Swift. Dot. Nope. T has no member. Is it default constructible or something? There's another protocol that we need to conform to. Oh, super annoying. There's got to be a way to... There's got to be a protocol for having a default constructor. I just don't know what it's called. Maybe string... No, string protocol wouldn't have it in there, would it? Initializers. No. I wonder if... Let's see what int conforms to in terms of protocols. Okay, well, okay. Our code is going to be a little bit less elegant. So, D. Okay, and let's turn this into a type. Okay, does that compile? Oh, yes it does. Okay. Okay, so, okay, so we have our data structure. What do we want to be able to do with this? We want to, because we're effectively assuming that this is a more or less infinitely large um, uh, kind of array of pairs, right? Except we're encoding it, so it doesn't really work that way. So let's actually do a map function, but only for a subset of things. So, um, begin. No. So we're doing our range. And using real ranges in Swift is kind of a pain because all the different, whether they have include or exclude the top things, they're all different types. And I think there's a way to kind of convert them to a canonical range type. But there's a lot of code to use ranges to allow people to use the range interface cleanly, which is kind of like strings are super cumbersome in Swift, even though they do what you want. Ranges are also kind of cumbersome to write an API to take, at least in my experience, because I've tried it a couple of times. Okay, and what do we want to do? And then we take a function which takes a t and returns a t. So we're going to transform every value within a certain range according to the function f. Actually, let's call it the transform. And it's a trailing closure, so we will largely pass it anonymously. And this is going to return us a self, right? Because it's going to be the same type. It's just going to have different values associated with things. So this is this function alone, I think, is the crux of our program here. So var new d. Again, let's just make sure we haven't gone off the... Oh, we have gone off the rails. Oh. Turn. And we've killed off the default initializer, haven't we? So we can't do that either, can we? We have to actually write an initializer. Yeah, so frustrating that we couldn't. Yeah, okay, fine. So write yet another initializer. This one explicitly named. Oh, we're still not there. Cannot. Oh, yeah, of course. So this is a... Yeah, okay. What are our warnings? Let's get rid of our stupid warnings. Come on. Hey, come on. Okay. Oh, yeah, let's can't believe I just didn't do this immediately. So we did that. ND was never mutated. We know that because we haven't written our function body yet. Okay, so I'm gonna write this in kind of an old style C way, and then we'll possibly improve the style later on. So we'll just use a loop counter. And we know D is never empty, so we can just start doing it without a bunch of crazy stuff. Well, no, okay. Begin. Okay, so we don't need to touch anything there. Equals D of 0. And we need to keep a previous value because at some point the range we change is going to end, and we're going to have to then revert to the value that was there before, right? Maybe this will become clear as we code it. Okay, so we know actually, let's do this incrementally so it's clear. Okay, so all those things stay the same. But now we reach the point at which our begin is in this range, right? So so now and we do an inversion from begin. Yes, it starts at begin, and its value is, we have to guard this by being at count though, I think. So that should be it to do. Oh, not D. DI 1. Okay, so at begin, we start heading towards the exit, right? And now, okay. And DI and is greater . Okay, now we're trying to find, how many ranges we affect, right? So this is going to be the last range that we're going to get up to the last range we affect. So for all these affected ranges, Uh, do, do, do. We're going to go up from the D. We're going to start there, and the value so we might be able to, this is just going to be the same as the above, isn't it? So we might be able to fold that in as a way of getting our to-do guard to work. There is an optimization opportunity here. And that's why I wanted the equatable thing. Should we actually implement that now? Let's hold off on implementing this. We might not even need it for this particular problem because the problem size is quite small. But I think this is quite an... It turns this into a generally good data structure as opposed to just a hack for a programming contest if you were to coalesce. Because then it would be optimal at doing what it's at the storage. So you wouldn't have a bunch of little ranges all encoding the same thing. If you just said, well, if the value with the prior range is the same, then you don't need that prior inversion point. Just lop it off and leave it. Actually, no, that is so trivial to implement. Let's do it. And then if to what is it? ND. Prev is this is all Prev. I actually don't know if you can invert these comma clauses. What we really want is to do something like this. Well, we want to learn Swift, so let's see if we can do something like this. Sorry, that goes outside the parens, right? Oh no, it's not quite right, is it? Forget it. And this could potentially be slow, so let's not compute it twice. That's why I made it a variable. Okay. If there you go. It's a little uglier than using let, but it works. So okay. So for I is less than count. So I don't think we need this at all anymore, right? Because we're doing it. Oh no, we need to take begin. Well, let's finish writing our code and then think it through. So, and finally, end is greater than. So now end is less. We're going to have to use this PV. We need to update it in various places, but again, we'll figure that out later. This is me taking my time and trying to talk through my thoughts, which is really slowing me down, man. So now what do we have? We have end is less than or equal to di, right? So we go from, so we need, and we've just done the prior thing, these are all the d's, and now we go to our end point, and we say from end on out, it goes to PV, right? So, PV. Say, no, we don't need that because we're actually doing it. Di1, and you know what? Just it's nice. Okay, so we've transformed part of that range, and now the rest of the range. D plus equals D. We just throw the rest on here, right? So I don't think we got the start right. So we still need to do a little thinking, but let's just see if this compiles, shall we? Oh, no. No member VO. We could have actually named the members of this tuple. We're using it so much. And we're taking our time now. But where is that? Line 22. No. Type T, yes. That's last one. So it compiles. So we have to check all our boundary conditions and everything, and I think we've done something a little funky at this beginning here. So what do? We find the first range we need to inject ourselves into. Okay, we find the first. No, I think we actually need our PV all the way back here. D. fine. So let's actually, an invariant of our entire type is really that D is not empty. So that's why we can do this, right? In fact, let's move the assertion closer just because it's good practice to show kind of what it's helping, right? Okay, so now okay, this might work. Let's actually, what are all these stupid, where are my prints coming from? We don't need that, but where, here we go. In fact, let's get rid of all our work, right? Because all this is useless. I'm taking a long time to do this because, as I say, this is like the crux. And I do think this is a cool data structure, sort of, right? So it all compiles. So let's say range dict of what type? Let's say strings. And our background will just be dots, right? Print map map range from 3 to 6 of, well, in this case, let's actually not even use our parameter here. So let's just see if this runs. Oh, no. Oh, how do you implicitly ignore can you do that? No. Oh, I don't even know. Okay. Oh my God. Missing expected. Everything about this is wrong. Oh, where am I? Where did those returns go? Oh, in. Okay, so it starts at 3 to, yeah, okay. Now let's try an overlap where I'm not going to write a full range of unit tests because we still are doing a programming contest, and part of that is not worrying so much about this stuff. But you can imagine, testing all the boundary conditions is just a matter of, putting in the work and getting it done. So 3 to, oh, it was 3 to 6, and then it's, oh, so I missed out. So I should have a 3 to 5 foo, and it's not there. So it's a good thing we did test this. So what are we doing? So what happens here? Append. So we should have if we just had a 3 foo, well, I is less than, I 0 is less than begin. So we should, oh, that's what, sorry. That is, in fact, the correct answer for the code that we provided. What we really want to do is then do another map range. What is that mentioned with? I think that's right. So what happens now? Oh. Can't have extra white space. Ooh, and it hung. So that's super interesting. So, while. Oh. Yeah. Plus equals 1. Let's try that again. Okay, 3 to foo. And then at 5 it turns into bar. And then at 7 it turns into dot again. Yeah. Okay. So, if that works, well, okay, so we might as well finish off this data structure here because we're going to need another operation, which is a like a version of reduce, because we need to count the number of lights that are on. So we could try to come up with a signature for some general purpose reduce operation, which I am kind of falling for this little data structure we're writing, so I might do that at a later point, but we only need it to do the counting now, and that's all you can really use it for, to be perfectly honest. So count and then we'll call it a pass a counting function, which goes from t's to ints, right? And it returns an integer. So all this is gonna do is okay, we're definitely for every one of these things. Yeah, okay. So every one of these values, how do you count the total? Yeah. Well, hold on. So there's going to be something about car 0 times that goes somewhere. We just have to think through like the 2 other lines of code that are going in this function. Okay, it's not car 0, it's car in D. The trouble is we actually need pairs of things. So we're going to write a C-style loop again. Um, I1. Oh, let's, okay. So we're going to say out plus equals out no d I minus 1 0. You see how I can't talk and think at the same time? It's must be so frustrating for you. So what we're saying is, so this is the entire range that we're looking at right now. And d is 1, and that entire range we're multiplying it. So that's how many we have there. Okay. What is my count func? Yeah, okay. Yep. That looks good. And then we do it, we have to special case one end, right? So oh no. X minus D. Okay, so just to do this, let's map range. And then we have to count. Right? How many are foos? Oh, if it's a foo, let's keep it all on a line. Because we're returning ints, right? Not bools. No, respecting 45. We do need to return, don't we? We could have actually, instead of updating out, just returned the sum, but whatever. Oh, should return. Oh, see how not thinking and talking is a problem. Oh no. So, we might have overflowed. What do we do? 1. Decount. Last. 1. Let's keep printing out, shall we? And see what happens before we crash. So before we crash, oh, we don't get anything. Count. Are we actually running with as much debug information as we can? Yeah, we can. Again, this is the problem with coding outside of thingy. Oh, hang on. Di minus is plus min. I think we might be overflowing here, so let num -1 that seems. Oh, what's not working? Oh, I keep thinking there's a thing there. Okay. And we got to do the same thing here. Oh. Yeah, okay, we got it. So out plus equals, oh no, hold on. It's this logic and x minus d. Last bang, okay. Yeah, okay, so 0, 3, 3. So 3 of them are foos, right? 3, 4, 5, right? And now let's do the same here to count the number of foos, which should be just 2, right? Count. Oh no. Count. And it's just 2. Okay, so let's get rid of this stupid print statement. Okay, so so maybe we have all the rudiments we need to implement our thing. I have no idea how long I've taken to do this. I've definitely been taking my time. So, what do we do? We definitely need all that, right? Except this on is now going to be a, what did we call it? A range dict. A range dict of, and that's our x-axis. This is our y-axis. This is our z-axis. And then it's just whether it's on or not. We didn't really try much with anything empty, did we? But sure, it'll work. Why wouldn't it work? Oh, ye of little confidence. Okay, why is this? BBEdit has a weird bug where when you comment something out, watch this. You commented, see, I have an indent of 2 spaces. You commented out. This is not a function I wrote. This is BBEdit's comment out function for Swift. You comment it out, looks good. You uncomment it, and it's moved a space to the left. You do it again, and it's all the way over to the left. This is crazy. So, yeah. Anyway, get on that rich Siegel? Mogul? Something? I don't know. Okay, so we have our 3-dimensional cube. So now we want to say on for everything in the range from, what is it? Nums 0 x coordinate up to nums x I've forgotten the format. Yes, nums 0 1 is the end, but -1 because now we're doing non-inclusive ranges, right? So for everything in that range, we are going to do a similar thing for the y-axis. Nums 1, and then do a similar thing for the z-axis. Ooh, we need our dot. Nums. Okay, and now we have to think through. So this needs to return it has to transform a t to a t. But I think we have the same issue here, and so we want it to go false if it was turned off, and want it to go true if we're turning it on, right? And I think that's our whole. What do you mean that didn't match? Oh, sorry. My fault. So I think that's our whole logic. Isn't that kind of beautiful? I say that without having run it. So let's see whether this, let's see whether it runs. Let's not bother trying to do anything clever. Error. Ranged equal does not conform to equatable. So why not? Unable. Why doesn't it conform to equatable? Oh, because I didn't say it should. But it should. Oh, now we have a whole bunch of interesting stuff. Stored property. Wait, arrays of tuples are not equatable? How are arrays of tuples not equatable? Let's check that. We can get around this. This is, yeah. Let's see how this is true. What were we doing before? A equals Okay, that's definitely a tuple, right? Okay. That seems to work. C. Let's say that is. Okay, so A equals B, no. A equals C, yes. B equals C, no. Okay, that all looks good. Now, we'll say AB, type cannot conform to equation. This is madness, I say. Madness. And we're gonna have to change all our code all over the place if we do this, but tuples are infuriating. Well, let's make sure we can do this with tuples before we do anything else. Struct. String. Oh, God. Okay, so, what? A. And this is C. Oh, I didn't make T unequatable. Oh. Okay, let's try this all again. Okay, now A is that. B is that. Right? And C is that. Okay. AB. False. Okay, now we do equals BC. Now it's equatable. So, yeah. Tuples are, I find them so frustrating because really what you just want to do is, what I wish a tuple were exactly what I'm doing now. You just do a struct, what are we going to call it? And what I wish a tuple were a struct with just a whole bunch of protocols listed out there or inferred from what you can actually build, so that you can then do and then let's actually let P let V is a T, right? And this is an array of entry. Entry of Oh no, we're gonna change the signature anyway, right? Okay, now we just have to change all these to this. Of which there aren't that many, but now what are the bets this is going to compile? The the very first time. Oh, we're going to make this an entry. And then we're going to build our entries here. I might be actually taking longer than I did last night, but I'm genuinely enjoying this now. Because I like this data structure we're building. We still don't know if this approach is going to work, because it could be too slow, in which case we need to rethink it. But, you know, you do what you got to do. 0p. Okay, how are we doing on this? Pretty close. Range dict var on. We need to initialize. So we got very far before screwing up. So, what do we need? We need a T. There's got to be a... See, this is why having a default initializer would have been much nicer, but for our purposes, this isn't so onerous, but it's a terrible API. Because as I checked earlier, the default constructor, the default initializer for Booleans gets you false. So we really just want to have a default initializer for all this crap. Missing argument. Oh no. Warning. Result of call. Wait. That seems serious. Oh no. I was wondering why it was so quick, actually. Right? So, it's fairly quick, but it thought. So, let us... now let's try running our count function, because we don't have any code below there. So now our count function, right? So on count. So our x-axis counts, our y-axis counts, our z-axis counts, and then 0, 1, 0, 1, 2, 3. Well, let's run some test data through this, right? Where are we doing this? Reading our lines. So, test one, yeah, okay. So I think this is the first that's provided. That doesn't seem correct at all. Nope. Oh no. So, what a shame. I would have felt so good if I had just nailed it from the very first run. Well, let's actually print. And see if this is comprehensible. Oh, it's very not comprehensible. Let's make this a okay. out append let's do this. Carp. Might that be a little? And of course we could actually do that in a more sophisticated way where we're not constantly appending, but I don't think it matters, at least in this case. So let's see if that's any more readable. It is. Okay, so we start there with false, and then at 9, we get false 9. Where do we find any truths? Okay, from 10 is true. 10 to 11 is true. Wait, 10 is true, 11 is true, 12 is false. So that means that our coalescing didn't work. This bit right here is, so it's false up to 10. And then at 10 it's true. And at 11 it's true, but we have separate points for those, but that's messed up. But also, okay, 11 is 1 true. Okay. This is looking like more than one. So I think our count function is broken, is the short story here. Out plus So let's, every time we call count, oh, sorry, not you. So we have -1. The very existence of -1 is not good. So out D I-1 position. Okay. Position. Let's actually well, okay, so how did we get that -1? -1. That is to false. 9 is false. Our coalescing function is definitely not working correctly. So we should check that. But that, 10 is true, 9 is false. Ooh, this is all, ooh, no. This is definitely not right. So, ooh, such a shame. Okay, so this function is broken as well. Okay, we have a bunch of entries. I is less. Okay, so begin less than or equal to V. No, we don't need that anymore. This isn't guarded by our thing. So let's so that's one of of the things that we saw going wrong. So we started at begin, right? Yeah. And is greater. And is less let's do it again, I guess. DI position is greater than end. So how do you ever get this thing of a smaller number that comes after a bigger number? Because that's the real trick here, isn't it? That they should always be increasing. So every time we append, let's let's actually make it clearer. And if those don't, then it's our final extension that's broken. So, oh no. What did we break? 40. What? Count, oh. And we have to do this in a bunch of places because we cut and pasted, don't we? Yeah. Oh, okay, and invalid. 51. Yeah. Ooh. this is quite ugly code, so we're now bordering on programming contest territory. 2. Oh, what is this? This actually might be our bug, right? New V, 2. I think we might have just hit our bug, but let's, oh, well, not quite, so we crashed at the, false, 10, true. So 0, 0, so we got all our zeros, and as soon as we were getting to a 1, I don't know what's going on. It's not going super well. This wasn't an assertion, at least. Let's just see how this is going. Yeah, so where are we going? We got a bunch of zeros. So this is in our count routine. Something is going wrong. Oh. How far are we getting? So at B in, so we got a giant number on our output. Why did that happen? Count. It's true, it's 1. Otherwise it's 0. A, so B in max. I think we're going to have to go back to our print self. And our, so, okay. 10 is true, and then we never turn it off. So that's a mistake, definitely. So how did that happen, that we never turned it off? Right? If Oh no. That's why. PV. I forgot what code we put here. We were saying the prior value. Or 2 is not equal to. Okay. And to prior. Oh. It's something is going on here. So this is where we end. Okay, so end is greater than. So now end is less than the next one. And the prior value is that. And should get the transform of the prior value. Oh no, what? No, hang on. What was I doing? We don't do this. Now, from end and prior value. Prior value. That seems better. Prior value. Is it P capital V? Yes, it is. Okay. Same thing here. So I don't know if we actually did find the bug here or not. Thought we had. Assertion failed. Well, that's nice. At 47. Okay. So. I'm just curious. I assume it's going to be the same thing. Now it takes it down to 53. We should really do something about this. Because because we shouldn't be doing this if it's empty ranges anyway, so there's something going wrong here. We're still doing it 53. Oh, I've taken forever doing this, but I'm genuinely enjoying it. I like the data structure I'm building. It seems much more general purpose than some crazy cubic geometry, and it seems like I'm just being kind of slow getting it right. Do 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 do. So, well, let's do this. Self. Right. Oh, but we're gonna get all these Uh, uh, this is unfortunate. Okay. Because we're making recursive calls here. So let's actually, where are we? It's at 53. So let's, oh, you know what? We could actually, yeah. Because that's kind of what assertions are for, isn't it? Begin, end. D. Yeah, okay. And well, sure, why not? Okay, can we figure something out? Oh. Oh. Okay. Okay, now assertion failed. So okay, we're just starting begin and end. Oh, because we're potentially doing empty ranges. Ah, all this is wrong. Now what happens? We're probably going to generate a huge amount of output. Now we get 39. So was that our we've spent all this time debugging that. It's nice getting a video of this because I can actually see how much of the time was doing that. So for the first one, 39 cubes are on. So we might be getting the right answers here. You know, let's try test 2. Right? Man, that was a lot of work to find a trivial bug. Okay, here's I think the larger example is test 2. And it should be 590,000. 784, yeah. Okay. So, let's go and try our real input. Well, we got it quickly, so I like my data structure. I really do. Even though it was a bit of a... it's a bit of a bear to debug if you're not doing real engineering. But, yeah, okay. I wonder how much time was just debugging those minus ones instead of plus ones. Because this is quite a long video for me. So it wouldn't have been a good time anyway, and I don't like to spend this much time at night because I'm sleepy. Anyway, I'll cut this here because I have real things to do today, and I spent forever doing this. But I will be back tonight, and maybe I'll reflect on what I've learned from this disaster. I'll see you then.